Hey gang, welcome back to Geo 2. This lecture is going to cover plate tectonics, which is lecture number 6, or PowerPoint number 6. We began this lecture on Wednesday, and we'll be finishing it on Monday, the 14th of February. It's kind of a long lecture, and so we got about halfway through it on Wednesday. We're going to finish up on Monday, and then there's going to be a review session on Wednesday. And we'll be taking the second exam next week. Monday of next week is a holiday, and so we'll be taking it on Wednesday. And just again to be clear, the exam will be either in person or online. You could take it either way, but you will need to take it during the class period. And so I'll send out a message on iLearn with specifics about how you're going to go about doing that. But in any case, we'll move on here with PowerPoint number 6 on plate tectonics. And that discussion really begins with this guy here, Alfred Wegener. He was a German guy in the early 1900s, and he's known as the father of continental drift, as it says here. And this idea of plate tectonics, everybody's pretty familiar with it at this point. You've at least learned about it at some point in grade school or high school. And it really is this unifying theory of the geosciences, of earth sciences. It really explains so many things about the Earth system and Earth's history that we otherwise wouldn't be able to reconcile. And so the first person to really point this out in earnest was this guy named Alfred Wegener, and he did it based on a few observations. They're listed here, but probably the largest argument was through fossil evidence, and that's what this figure down in the bottom left here is showing. He also argued that the continents just seem to fit together like a puzzle, right? South America and Africa. There are other similarities that cross continents, like rock type, and there's this paleoclimatic evidence. And so if we go one by one through these, the argument that he made is basically this: these colored areas down here in this figure represent the distributions of particular fossils in the rock record. And as you can see, their distributions seem to cross modern-day ocean basins without spreading out on the continent. And so, how could an animal, some organism, have lived in Central South America and Central Africa, but not Northern or Southern South America or Africa? This seems quite problematic, right? Unless this animal is a very good swimmer and just liked to swim across the Atlantic Ocean, it doesn't make a whole lot of sense as to why you would see this distribution. There are also similarities in rock type and structures on either side of the Atlantic Ocean. And so in particular, there's a mountain range right in here, kind of in Morocco on the northern portion of Africa. It's called the Atlas Mountains. And it is genetically related or related in origin to the Appalachian Mountains on the eastern side of North America. There's also a mountain range in the UK known as the Caldonides. That is also related to the same mountain building event that created all of those. There are in South America and Africa, there are lava flows that can be connected across the Atlantic, and so these are really hard to explain if you don't accept the idea that the continents could have been moving around in the past. All right, and so scientists at the time tried to explain this. Right, and they didn't know that continents had the capacity to move, and so they explained it the only way that they could think of to do it. And they said, well, at some time in the geological past, sometime in Earth's history, there must have existed these land bridges that connected continents across ocean basins. This was they were the so-called Gondwanian or Gondwanan land bridges. Okay, and this is obviously not correct, right? We know today that animals were able to migrate freely from South America over to Africa, not because there was a land bridge connecting them above the Atlantic Ocean, but because at some time in Earth's past, South America was right against Africa. Okay, now Alfred Wegener went a step beyond this, and he came up with a reconstruction for the past 300 or so million years, going back to the late Paleozoic. And he said, look, all the continents seem to just have smushed back together and become this single landmass, which is not too far from the truth, honestly. This reconstruction is not correct, but it's not horribly incorrect either. You had a lot of pieces together there. Another piece of evidence that he pointed to was paleoclimatic evidence. By this point, people had traveled to pretty remote regions of the Earth, and what they found was that there are rocks and fossils there that don't fit with the modern climate. An example of this is fossils of palm trees on the coast of Antarctica, which exist, and that reflects deposition at a time when Antarctica was either not in its current position, or the climate was very, very different. It was warm enough to sustain palm trees at the poles. Okay, and so scientists of the day came up with ideas to explain these things, like land bridges, other things. Alfred Wegener said, no, that can't be right. What if the continents actually moved throughout Earth's history? And he reconstructed it like that. The scientific community did not buy this. They objected. The scientific community is often slow to adopt new thinking, and in this, this was no exception to that. And they objected. Their main objection was that Alfred Wegener didn't come up with a mechanism that could drive continental motion. And so the workers at the time were imagining these continents just kind of plowing through ocean crust. And that didn't make a whole lot of sense. Certainly we can't see them doing that on human timescales. But shortly after, a man named Arthur Holmes in the 30s, he suggested that perhaps convection cells operating in the mantle could provide the force or the motion necessary to produce this continental drift. Okay, and he came up with this model of large-scale convection cells operating within the Earth's interior. Okay, and these would be transferring heat energy, like it says at the top there, by circulation of a liquid or a solid that's being heated from below, right? Just like any other version of convection. You have a heat source from below, hot material rising because it's less dense than its colder counterpart. It cools as it moves away from the heat source. It moves laterally, continuing to cool until the density gets high enough that it sinks. And then it returns to the heat source, travels laterally, gets heated up, rises, travels, and sinks, just like any other convection cell. Okay, and it turns out that this is the case. Indeed, there is a region of the mantle known as the asthenosphere. It's the uppermost mantle. It does convect. It is not a liquid. It's a solid, but it does experience convection. We use the word plastic often, plastic deformation or a plastic solid. It's kind of like a silly putty or something like that. That's very clearly a solid, but it's capable of flow and motion. And it's in that state because of the immense heat and pressure that materials experience as you move downward into the Earth's interior. It gets hot and the pressure gets intense. And so despite the high heat, this material exists as a solid because of the confining pressure. Okay. So in the early 1900s, Alfred Wegener came up with this theory that the continents appear to have drifted throughout their history. Okay, and Arthur Holmes, Alfred Wegener, Arthur Holmes came up with this idea that the convection of the mantle could drive this continental motion. He came up with that idea in the 30s. However, as this bottom point says, very little light was shed on this hypothesis between the 30s and Alfred Wegener's death in the 50s. Holmes obviously proposed mantle convection in the 30s. So today we do understand how plate tectonics works, and we have an enormous body of evidence that demonstrates its validity. And we're going to walk through a few pieces of that evidence in these slides. But the first major advance in this study was it came from in the form of paleomagnetism. And what I'll say is that a lot of scientific advances came from come from wars generally, but World War II in particular really pushed science forward. It did so for a number of reasons. It really pushed the earth sciences forward, mainly because World War II was the first time that countries used submarines. And if you're trying to use a submarine, trying to sail in a submarine underwater, it would be wise if you understood what the conditions underwater looked like. So techniques were developed to image the seafloor, create high-resolution maps of depth, something we call bathymetry, so high-resolution bathymetry maps. And there were also advances in detection equipment, right? If your enemy has submarines, then you might want to develop a technique that you can employ to locate the submarines. And so through that science, a great deal was understood about magnetism. And basically, the Navy was dragging around giant magnets or giant magnetometers behind boats, measuring the magnetic properties of the subsurface of the ocean and the Earth's crust beneath, looking for anomalies, being submarines, right? And so a lot of science was. Well, we're going to talk about a few different things that were developed through the war, but yeah, paleomagnetism was a big one. Okay, and this concept really provides the foundation, at least a foundational piece of the evidence that demonstrates plate tectonics. And so we've all used compasses in our lives, and a compass is just a flat dial that has a needle on it that's magnetized. And we all know that if you take a compass and you turn like this, the needle turns until it finds north, right? And then wherever you turn, the needle will always point north, right? What you might not realize is that what's actually happening there is not that the needle is pointing north, so to speak. What's happening is that the needle is actually aligning itself with the magnetic field lines that it exists in at that time, okay? And so we're all familiar with it pointing north, all right? That's known as the declination, all right? It provides a direction. But there's another property of a compass needle that you might not be aware of, and it's called the inclination, all right? So just like the compass needle points like this, north and south, it also moves like this, up and down. The slope or the inclination changes. And that changes as a function of the magnetic field lines, but those changes as a function of where you are on the Earth's surface relative to the poles. And you'll see that in just a moment, exactly how that works. But what's important to note before we sort of jump into that is that there are many, many minerals on the Earth's surface that contain lots of iron. All right, and iron can be magnetized. It isn't always, but sometimes it is. And when these iron-bearing minerals that are magnetized are cooling from a magma, all right. So a magma erupts from a volcano, and this lava flows, and it begins to cool, and minerals begin to crystallize out of that magma. As those minerals begin to crystallize, they grow in preferred directions. Also, the iron within those minerals, when it's very hot, it has the ability to move around kind of freely. But as it cools, it begins to crystallize and be locked into position. Okay, and so if you take a molten magma or a lava that has a lot of iron in it, and you put it in a magnetic field, which exists everywhere on the planet, When it's hot, all of those iron-bearing minerals, all the iron in those minerals will align with the field, okay, the magnetic field. And as it cools, it crystallizes and it's locked in. Now, that magnetic orientation is locked in with everything else. And so if the magnetic field were to change after that rock had cooled, that change would not be recorded by that mineral. The mineral would still be pointing its little compass needle at the old magnetic field. Okay, and that's really important because we're able to date rocks with very high precision. And if we're able to measure these magnetic orientations, then we could learn something about the magnetic field in the past, or perhaps the continents. All right. And so if you do this, and you go around and you measure a lot of these orientations, what you find is that the magnetic pole appears to have moved dramatically throughout geological history, or perhaps the continents have moved. Okay, and so here's how this argument works. If you say, let's say we have the Earth. Here's the Earth. All right, and we have, let's see, we have the North Pole up here, right? This is north, and this is south. All right, let's say we have some continent over here. There's our continent. This is continent A. And on continent A, there's a volcano. All right, there's our little volcano. And through time, it has a number of lava flows. There's one lava flow, there's another lava flow, there's another lava flow, all right? And they're all kind of stacked up together, all right? So we have a continent, it's got 3 lava flows, and they're all kind of stacked up on top of each other. And if you go from the bottom to the top, one can assume that we're moving from the oldest lava flows to the youngest lava flows, right? That's that law of superposition if we go all the way back to James Hutton, right? So if we look at the oldest lava flow, well, let's start with the youngest lava flow, okay? The youngest lava flow, if we look at the magnetic properties of it, it's pointing straight at the modern day North Pole, okay? Now, if we move to the next oldest lava flow, you might also expect that it's pointing towards the North Pole. But what you might find is that it's actually not. It's pointing over this direction. And then if we look at the oldest lava flow, perhaps the magnetic orientation of those minerals is pointing that direction. All right, now this implies something. It implies that perhaps the North Pole has moved, right? From there to there to there, or from here and 1 and 2 and 3, right? But there's an easy way to test this hypothesis. This, by the way, would be something we call true polar wander, right? Like it says there at the bottom, versus true polar wander. If the pole was actually moving, that would be true polar wander, and that would look something like this. However, we can test this pretty easily. All we have to do is go to another continent. Okay, here's another continent, continent B, right? And we find a volcano on continent B as well. And there are some lava flows, right? A couple of lava flows, maybe 3 of them again. And now if, we'll go back with N1, N2, N3. Now, if the pole actually wandered, let's assume that these lava flows are the same age, roughly, as the lava flows on continent A. This is continent B. If the lava flows are the same age, they should be pointing to the same poles, right? And so if this is the youngest lava flow here, it's going to be pointing to the present day North Pole, okay? Now, if true polar wander existed, our hypothesis here, right, would be that lava flow number 2, we'll call it this one, should point this way towards N2, and lava flow 3 should point this way, right, toward pole number 3, okay? However, that is not what you will find if you go out and you measure and you make these measurements. What you'll find is actually that these are not pointing at the same past paleo poles, okay? What you find is that they're pointing in completely different directions, All right. Now, if this is right 1, 2, 3, and this is 1, 2, 3, right? The only logical explanation here, right, is not that the pole moved, right? Because that's inconsistent with this arrow here, right? And this one for that matter. That's not a consistent interpretation, right? The only consistent interpretation for this is that this continent has rotated, right? This continent has rotated this direction, and this continent has rotated in this direction, right? Two independent motions, while the pole remained in one place. And that's called apparent polar wander, right? Because the pole appears to be wandering if we investigate the magnetic properties of the rocks on these separate continents. The pole appears to be wandering, but what's actually happening is that the continents themselves are moving. Okay, and so that was sort of the first piece of evidence, and the science of paleomagnetism has come a very, very long way. There are hundreds, maybe thousands of individuals around the world who do this practice, and they have reconstructed a very detailed record of Earth's history. All right, and so let's see. Okay, this is just the same slide. So the Curie point is this. So it says here, iron-bearing minerals, when they cool below the Curie point, act as fossil compasses that point toward the existing magnetic poles. And so the Curie point for iron is around 770 degrees centigrade. Atoms that behave as tiny magnets spontaneously align themselves in certain magnetic materials. I don't think that that's actually a very good way of describing it. How I think about it is more that above this temperature, those magnetic materials are able to align themselves because they can move freely. But once they get below that temperature, they're kind of frozen, right? They're crystallized, and they're unable to move anymore if the magnetic field changes. All right. Okay. So the Earth has a magnetic field. Where does it come from? Let me see here. So I was looking for a figure that, let's see. Let me see if I can grab it because, okay, well, first, we'll look at this first. Okay, so the Earth has a magnetic field. We all know that. At least most of us know that. It does, that's true. And it has it because of the state of the Earth's interior. Oops. And so the Earth's interior is differentiated. It's not all the same on the Earth's interior. And you might wonder how we know that, and I'll talk a little bit about that in a moment. But the Earth's interior is made up of a mantle and a core. And the core is made up of an inner core and an outer core. Okay, and the inner core is solid. It's made of a nickel iron compound primarily. The inner core is solid, and the outer core is liquid. Okay, and anytime you have metals moving past one another like this, you generate electric and magnetic fields. And so that's essentially what a generator is. So this is just a little hand cranked generator. And you spin this wheel and it spins these copper coils that are inside this magnet here. And so that's how you generate electricity. You spin this metal core inside of a magnet. Okay, and that's how electricity is generated. Similarly, if you just have metal here and you move some metal around inside of other metal, you induce a magnetic field. All right, and so through that induction of magnetism, you generate a magnetic field, right? Okay, and so magnetic fields are interesting for a bunch of reasons. This isn't a course on electricity and magnetism, so we're not going to delve as deeply as you would into this stuff if you were in a physics class. But magnetic fields are pretty interesting, and we do want you to be familiar with them because they're pretty important. All right, and so Let me throw this out here. I don't know if it's going to work. Yeah, there's a picture. All right, and so if you go online, you can find a million videos on YouTube of people putting iron filings. So if you took like just an iron nail, like a nail you know pound it to build a house or something, and you file it down, and you make these like little filings, little bits of iron, and then you sprinkle them over a magnet. So this is just like a standard bar magnet. It has a north and a south end, right? It's a magnet. Everybody knows magnets. If you sprinkle these iron shavings, this magnetic material, over this magnet, you might expect it to just get attached to the ends of the magnet, but that's not what happens. What happens is that if you do it very delicately, what you'll find is that all of the iron filings will align themselves in the magnetic field. Okay, and the magnetic field is this field that has these field lines that go from south to north, really, but they do so in these kind of concentric bands. All right. Now this is I think okay. So this is pretty interesting, and it's getting us toward what I was talking about earlier with inclination and declination. All right. So if this is what the magnetic field of the Earth looks like, right? We could just draw a circle here around it. And in fact, I think I actually put this figure on here. Hey, I did. Look at that. All right. So, well, we could put it this way. So we have the we have the Earth here, and there's a couple of poles. Oops. Let's do that. We've got a couple of poles, a north pole here and a south pole here. Okay, and the magnetic field is running from one pole to the other. What you can see is that if we place a compass, right, anywhere on the Earth's surface here, it's going to point toward the North Pole, right? That's the declination, right? The declination is always going to point north. That's what compasses do, all right? But the compass needle also has an inclination, right? And what you can see is that at the poles, the magnetic field lines are going almost vertically. Let's get a different color here. Let's take red. All right. At the poles, the field lines are intersecting the surface at a very steep angle. But as you move to lower and lower latitude, those field lines begin intersecting the Earth's surface at a shallower and shallower angle until you're out here at the equator. At the equator, right, they intersect at a right angle. Is that clear? Right? And as you move towards the South Pole, they get steeper and steeper and steeper and steeper until eventually at the pole, they're vertical. Okay? This is true. And it's how compasses work. It's so true that if you go deep into the southern hemisphere, if you go to Antarctica and you want to do earth sciences, you want to read a map, you want to not get lost on Antarctica, and you're using a compass to navigate, you have to have a special kind of compass, because if you don't, the needle angles itself so much that it starts hitting the housing of the compass, and it disrupts the operation of the instrument there. You have to have a specially made compass in order to for it to operate at those high latitudes, and that's because of this, because the Earth's magnetic field does not intersect the surface at the same angle everywhere you are. It depends on your latitude, all right? And that's a really interesting phenomenon generally, but it's really important to the earth sciences because it allows us to reconstruct the path of continents in the past, the past trajectory, movement paths of continents, all right? And so if you look at the Earth, it sort of looks like this. This is just a nicer kind of infographic-y drawing of this. The field lines, again, are coming out at more or less a perpendicular to the surface at the poles, and at the equator, they're more or less horizontal. And in between the two, the steepness gradually increases, okay? And so if we go, if we go to a magmatic rock somewhere, and we are, we very carefully sample it in the field, we take it back to a laboratory, noting the very precise orientation of that rock, where we found it in the field, where it originated. We take it back in the lab, we measure the magnetic properties. It tells us two things. It tells us at the time that that rock crystallized, what direction was the pole, and how far away from it were we? What latitude were we at? Okay, and so if we can go to a place where there's been a volcano that's erupted repeatedly throughout Earth's history, which is very common, right? Volcanoes erupt periodically over and over and over again for the amount of time that they're active, right? And some volcanoes are active for very, very long periods of time. There are also lots of volcanoes, lots of volcanic rocks. And so by investigating this, we, as a community of scientists, have built a record that goes back hundreds and hundreds of millions of years, reconstructing the path that continents have traveled. All right, so that's paleomagnetism. The interior of the Earth. You might be wondering how we know that there is this solid and liquid core. And so this slide is showing you the interior of the Earth, right? It's about 6,500 kilometers thick, something like that. The mantle is the upper about 3,000 kilometers, and the lower 3,000 or so kilometers is the core, all right? And the inner core, again, is solid. The outer core is liquid. That has to do with the temperature and the pressure. But you may wonder how we know that. That's important. Seems like something very difficult to ascertain, because we've obviously never been down to these kind of depths in the Earth's interior. We can drill 10 kilometers, maybe 15. I'm not sure what the deepest borehole ever drilled was, but I would be shocked if it was over 15 kilometers. It could be 20, but the Earth is 6,370 kilometers thick. We're not getting anywhere near through the crust up here. The crust is between, it says here, 5 and 50 kilometers. We'll hear the numbers 5 and 35 kilometers. Depending upon what type of crust you're on, it can be 5 to 35 or so kilometers thick. Down here they say 70. That would be a very, very unique, maybe the Himalaya. The Himalayan plateau is maybe 70 kilometers thick, but in general, the crust is pretty thin in comparison. Now, how do we know this? Well, that comes down to seismic studies. All right, and so we live in Southern California. We've all experienced earthquakes here, and we've all probably seen seismometers, the little wiggly lines that come off of these instruments that measure motion in the earth, seismometers. And they look something like this. There's kind of a line, and then there's this wave, and then another wave, and like that, something like that, right? And what these are, this is known as the P wave, and this is known as the S wave. Some people call it the primary and the secondary wave. I think that's what those terms really refer to, the P wave and the S wave. But they're two fundamentally different types of waves traveling through the Earth's crust, or through the Earth. And they're fundamentally different types of waves. They operate different physically. The primary wave, the one that arrives first, by the way, they arrive at different times because they travel at different speeds, different velocities through Earth materials. Okay, and so based on the difference in time at individual receiver stations, the difference in arrival time of the P and the S wave, you can calculate how far away that event was, the earthquake occurred. And if you do that from multiple locations, then you can triangulate the exact location of that earthquake. And that's how that work is done. But there are two separate, fundamentally different types of waves, P waves and S waves. P waves are pressure waves, and S waves are shear waves. Okay, so imagine I have a slinky. All right, a little spring toy. Get in front of that here. All right, got a little slinky. There are basically two different types of waves I can produce with a slinky, with a big spring. Let's say I have a friend that's way over there, and I'm holding one end of this spring, and they're holding the other end. I can take the spring and I can go like this, and it's going to create this wave that travels like this, up and down. All right, that's one type of wave. That's a shear wave, okay? Because as I move the material up, it pulls on the material in front of it, right? I pull this up and it pulls this up, and then that pulls this up and that pulls this up, and then elastic forces bring it back down. It's shearing, okay? Shear force is a type of force where things are pushing and pulling at the same time on different parts of the material. So if I took this pencil and I put a lot of shear force on it, a lot of shear stress, I'm going to start to bend it, and it's going to start to stretch. It's going to be bad for the pencil, right? If I let go of it, some amount of that strain will rebound elastically. It'll sort of come back to its previous position. A lot of it won't. It'll be destroyed, right? But a lot of that deformation will actually rebound elastically. All right. It does that because it's a solid, and the material is in solid phase. The other type of wave that we can produce is a pressure wave. So if I had that same big spring, the slinky, and instead of going like this, I went like this. I pushed it. It's going to cause this compression that's going to travel as a wave through the spring. It's going to compress and then uncompress or decompress, right? And that compression wave is going to travel through the slinky to the other side. It's going to reflect and come back. That's a pressure wave. It is distinctly different than a shear wave. All right, the stress and resulting strain that the material, a slinky in this case, experiences is completely different. All right, one of them is shear force, where one part moves up and it pulls the other part up. All right, and they move down. All right. That's shear stress. The other one is pressure, where it compresses and then compresses and then compresses, compresses. It's a very different form of strain, and it results from a different form of stress. The point here is that pressure waves can travel, or compression waves can travel through basically any material. Sound is a good example of a compression wave traveling through air. All right, you can't hear in a vacuum. There's no sound in a vacuum because there's no medium for that wave to travel through. Sound is a pressure wave. Shear waves do not share that characteristic. They cannot travel through any substance. They can travel through solids quite well because solids have this elastic response to shear energy, or to shear strain, really. However, if you try to put a shear wave into a liquid or a gas, it doesn't travel because liquids and gases don't have shear strength. That would be the material property that we need in order to propagate a shear wave. Liquids and gases do not have shear strength, right? I can take the pencil and I can put shear stress on it, and I can cause it to strain, to deform. But if I took a liquid and I tried to do the same thing, it just falls apart, right? Or a gas, it just falls apart, right? I'm creating compression waves in a gas right now by talking, right? They travel just fine. But a shear wave does not, okay? Now this all, it all pertains to the study of the Earth's interior. And so how do we know that the outer core is a liquid? Well, we know that the outer core is liquid because of this, because if we have, let's grab a new one, we have the Earth, let's get the Earth here, right? And we have an earthquake somewhere here, right? There's an earthquake. And these waves are traveling through the Earth's interior, and they're being picked up by seismometers all around the Earth, right? Now, if they're the P waves, right? The P waves arrive everywhere, as do the S waves, P plus S, right? The S wave arrives a little bit later P plus S. However, if we get, this is my little Earth. It's not a very good drawing. I'm not a great artist. All right. When these waves intersect the core, they refract a little bit and they come through and they arrive at the other side of the Earth at some seismic station over here. But all we get is a P wave, right? Same thing happens. Same thing happens here. Only a P wave, right? And all of these stations down here are only going to see P waves. This is called an S wave shadow. All right, and what all that is to say is that there is a shadow down here in this region, right? This whole region, basically right in here. There's not going to be any S waves that arrive there, and that's because S waves, shear waves, can't travel through a liquid, right? So that is the main piece of evidence that was used initially, at least, to prove that the Earth's interior contains a liquid layer. We have shored that information up with other techniques, gravity measurements, a number of other techniques. It's also stands to reason from a sort of first principles approach that this should be the case. All right, so this so that kind of goes through what paleomagnetism is. All right, so when did we kind of realize that this was telling us something about the seafloor? That takes us to the 60s with this guy named Harry Hess. And Harry Hess was a Navy captain in World War II. He was also an earth scientist, and he came back from the war, and he had he'd spent a lot of time in the oceans, and he got a job on the faculty at Princeton University, and he continued studying what he had been studying really during the war, which was the ocean and physical oceanography. And he came up, he was looking at all this new data, these new data types that were being produced, and he came up with this theory that these topographic differences, these differences in the seafloor, the depth of the seafloor, were reflecting specific features that related to the Earth's interior. And in particular, he said, there are these giant ridges that seem to go up the centers of every major ocean basin. And I think that they represent the upwelling portions of convection cells in the mantle. And he said there are also these really deep portions, these trenches, that occur kind of at the margins of many of the ocean basins. And I think maybe those reflect the downwelling portions of the mantle, of mantle convection. And so again, we get back to this idea of convection in the mantle, and that these high portions of the seafloor reflect the upwelling zones, and these lowest portions of the seafloor represent these downwelling limbs. Okay, so this implies a couple of things. For one, it implies that the ocean floor is moving. Okay, it also implies that it's young, that it's being constantly refreshed. Because if these high points in the center of the ocean basins, like you see here, this oceanic ridge, if that represents the upwelling portion of the mantle, well, what that's really implying is that this is fresh, new material that's being generated through upwelling of magma and cooling and solidification at the surface. Okay, and if these are downwelling portions, these trenches, well then, where does the material go? It gets consumed or forced back into the Earth's interior. Okay, and indeed that's what's going on. Okay, and so a few years later, after Harry Hess came up with this theory, the idea of seafloor spreading was verified by a few studies, but the really seminal study was this Vine and Matthews 1963 that really set the stage for modern style plate tectonics, the study of it, the concept. And so what Vine and Matthews looked at, they said, well, if this material at the ocean ridge is fresh, it's being created all the time, and materials being consumed or destroyed at these trenches, well, then as we move away from the ocean ridge in either direction, the material gets older. And as it gets older, it should have the same, it should contain the same magnetic properties. All right, and so there should be some type of symmetry, some type of symmetrical distribution of magnetic properties as we move to to either side of the ridge. And they said, well, there's sort of one more piece of information here that is really quite helpful. Is it behind there? Oh my goodness, there's all kinds of things back here. Hang on one second. Goodness. Okay, so this, if you go out into a big stack of lava flows, and you measure the magnetic orientation as you move up through this pile of lava flows, just this one flow on top of another, on top of another, on top of another, right? And so as we know, that's reflecting the passing of time, all right? And if you look at the magnetic properties of those lavas, what you find is that they do indeed reflect the orientation of the magnetic field when they crystallized, but the orientation of the magnetic field hasn't been the same throughout Earth's history. It's reversed periodically. It's not a regular periodicity. It's kind of sporadic, kind of random, but it does reverse. It reverses on timescales of something like 1 million years. So this is age in millions of years ago, moving from the present 0 down to 4 million years ago. Currently, we're in this normal epoch, that is to say, normal polarity. If you go back about 750,000 years or so, you get these little switches, and then you end up in this long reversed polarity epoch. And so when the polarity reverses, that's probably what this was. When the polarity reverses, it's not like the Earth moves. The Earth certainly doesn't move. Just the magnetic field reverses. And so it appears from all the evidence that we have that what happens is it sort of just gradually weakens. It gets kind of randomly oriented during the reversal, and then it sort of fixes itself, and the poles are reversed. Okay. Magnetic reversals, as recorded in volcanic rocks preserved on land for the last 75 million years, are on here at the right. So this is just this very little bit at the top here. And what you can see is as you move back through the last 75 million years, it looks more or less like a barcode, right? And so if you have rocks of that age anywhere on the Earth, you would expect to see a very similar barcode, right, based on the age. All right, and so if you go out to what's the last one here? Oops. The magnetic field, by the way, is very important for deflecting solar wind, which many people believe would cause erosion of our atmosphere if we didn't have it. There's some debate about that, some controversy, but a lot of people believe that's sort of the conventional wisdom, is that without our magnetic field, our atmosphere would be eroded by solar wind. Okay. So the last reversal was around 780,000 years ago. They take about 5,000 years on average to complete these reversals, and they're separated from one another by hundreds of thousands to millions of years. It's highly variable, more or less random. Perhaps some relationships to extinctions. I'm not so certain that that's really true. The Earth's magnetic field serves to deflect most of the solar wind, whose charged particles would otherwise strip away the ozone layer that protects the Earth from harmful ultraviolet radiation. Okay. So getting back to Vine and Matthews, 1963, alternating stripes of normal and reverse polarity that roughly parallel the mid-ocean ridge with a symmetrical pattern defined by the ridge would be evidence of seafloor spreading, right? New basalt, so basalt is just a type of rock. It's the type of rock that makes up the seafloor. New basalt is added to the ocean floor at the ridge, and it becomes magnetized according to the magnetic field present at the time, right, as it cools below that Curie temperature, right, the Curie point. Okay, and so this is a sort of a conceptual figure of this Vine and Matthews kind of argument. And it looks like this. We have a mid-ocean ridge in the center here, and the crust is moving away from the ridge in both directions, right? New ocean floor is being created at the ridge as magma erupts, right? As it cools, its iron minerals are magnetized. New rock forming today would have normal polarity. However, these rocks here, they formed at a time in Earth's past when the Earth's magnetic field was reversed. And so they record reverse polarity. And if you look at either side of the ridge, you see this symmetry, right? And if you compare that, if we can get back to this, if you compared that to this, oops, yeah, this, what you would find is that it reflects, the most recent so many years, some number of years on this long barcode of the Earth's magnetic field. Okay, you would see that barcode on both sides, moving away from the ridge axis. And this is true. This was the sort of the first piece of evidence. Vine and Matthews. It's a classic paper, super important in the earth sciences, and it really established the first piece of physical evidence for plate tectonics. Okay, and subsequently we've gone out. I mean, for the last many decades, we've been operating the IODP and other oceanic scientific drilling programs. They're international, intergovernmental organizations that drill ocean floor, drill through sediments and crust, in order to do science and learn about Earth history primarily. And so there have been many expeditions that have drilled the ocean floor and recovered materials. People have done all sorts of really interesting science with those materials. But one thing that they do routinely is date the material. And so we have a very good idea of the age of the ocean crust throughout the world's oceans. And this is a map of it right here. And so the age of the ocean floor in millions of years, going from these red colors, 0 to 2 million years, back to the oldest ocean crust present at the surface today is about 200 million years old, right? And it's present in these spots, these particular spots off the north coast of Africa, off the east coast of the United States, out here in the Western Pacific, down here around Antarctica. They're very specific spots, and what I would tell you right now is that they're sort of the deepest spots in the ocean that are not trenches. So trenches get very deep, but this material, like this big kind of flat area here in the Western Pacific, that material is really old. It's 200 million years old, give or take, and that means it's had 200 million years to cool from a molten rock when it erupted at the mid-ocean ridge until today. It's had a long time to cool. And what happens to any material when you cool it, basically any material, it gets denser, all right? And so you see this topography where the mid-ocean ridges, these very young rocks, sit up really high. It's because they're really low density because they're really hot, okay? And as they get older, they're pushed away from the mid-ocean ridge and they cool. And as they cool, they become denser and they sit down lower. And so if you go out and you look at the bathymetry, right, the depth of the ocean all around, what you find is that over these mid-ocean ridges, the ocean depth is something like 3,000 meters. But if you go out here into these older, colder, denser ocean crusts, they sit down about 5,000 meters below the sea level, okay? And that's just because of density and buoyancy. See, repeating concepts. All right. So in 1968, continental drift and seafloor spreading were united into a single unifying theory of plate tectonics. you know. So this plate tectonics really is the unifying theory of the earth sciences. You know, physics is still searching for theirs. You know, string theory and those things may hold some promise, but if you're in the earth sciences, they found the grand unifying theory of the earth sciences in 1968. It's plate tectonics. Without plate tectonics, so much of the earth doesn't make sense. But as soon as you understand that on time scales that are not observable to humans, but certainly relevant to the history of the earth, large scale processes occur. They occur very slowly, but they have profound implications. This is one, right? Or the one, really. All right. And so, you know, today we know that the lithosphere, that's this region of the Earth that's defined as the crust and the uppermost mantle. The lithosphere contains about a dozen individual plates, maybe 2 dozen, that contain ocean floor, continental crust, some combination of the two. What you've, I think, already learned in lab is that continental crust and ocean crust are compositionally different. They're made of different minerals. Their chemistry is different, and because of that, their densities are very different, for one thing. But they reflect different processes. Continental crust is kind of like pond scum. You know, it's like that frothy, bubbly stuff that ends up on the surface of water. It's just sort of like a residue, and it's created through multiple generations of melting and eruption and cooling, partial melting, eruption, and cooling. And by doing that multiple times, you create an evolved chemical composition. Okay, and the bottom line is that ocean crust is made up of what we call mafic minerals. Those are minerals that contain lots of magnesium and iron, and they're very dense minerals in general. They're also very dark in color generally. Basalt is black for the most part. The continents are not made up primarily of basalt or mafic minerals. Generally, they're made up of what are called felsic minerals. And those are minerals that are rocks that are rich in feldspars and quartz, or silica. Quartz is just silica. And so continents are made up of these felsic minerals, which are significantly less dense than mafic minerals. And that has a direct implication, just like buoyancy everywhere, that has serious implications for buoyancy. And so once we get further into this discussion of plate tectonics and plate boundaries, what you'll find is that plates do or do not respond in certain ways based on their density, based on their composition. Okay. It also has implications for the thickness. You know, the thickest ocean floor we see is about 5 kilometers thick. Continental crust, on average, is about 35 kilometers thick, and like we said, it can get up to 70 kilometers thick. What's keeping that from sinking back down into the Earth's interior? Well, the fact that it's made up of less dense minerals. All right, and so while, if we go back to this figure here, the ocean floor is really young. The oldest ocean crust we have on the planet is only about 200 million years old. The Earth itself is 4.5 billion years old, right? So whatever that is, 22 times older than the oldest ocean crust. But if you look around the continents, we have materials on the continents. We have continental rocks that are 1 billion years old, 2 billion years old, 3 billion years old. There are rocks on Greenland that have been there for 3.5 billion years, right? Why are they able to stay so long at the Earth's surface? Well, it's because they're lower density. And so the processes that consume ocean crust back into the Earth's interior, recycling it, do not operate on the continents. Continental crust cannot be consumed back into the Earth's interior because it's too low density. It's like taking a balloon and trying to put it underwater, right? All right. So I'm going to stop it here, and I will I'll record the second half of this lecture this afternoon and get it uploaded to you guys. But this is a pretty good place to stop. We talked about sort of the history of plate tectonics and the evidence that's used to establish it. We talked about paleomagnetism, the importance of the magnetic field. We also talked about the evidence, the fit of the continents, the distribution of fossils, the evidence that Alfred Wegener initially used to suggest that continental drift was a thing. On the second half of this lecture, we're going to get into the plates themselves, talk about continental cross and oceanic cross a little more specifically. We'll talk about the plates and their boundaries. We'll talk about what these different kinds of boundaries can look like. There are 3 types of them that we'll talk about, and we'll talk about other sort of implications like earthquakes and volcanoes. And yeah, so I'll see you guys next time. Thanks very much.